to introduce characteristics about any sensors. Okay, any sensors we want to compare them, we have to use some criteria to judge them. For example, sensitivity we just introduced. Let's say sensitivity is the most important in your case, then we just pick up the best sensitivity from the market and apply to your applications. And we do have other characteristics or parameters we want to discuss today. So first one I already introduced, noise and resolution and transfer function, so many. Okay, very easily to get confused. So basically I invented this graph. Okay, you call Jung's graph, Jung's figure. Okay, anyway, so I summarize everything on this graph to describe this much characteristics in one graph and give you some better way to understand what are the difference of them, what are the definition about them. Okay. All right. So we have input, output. Okay. Basically, it is input output model we just introduced for any type of sensors. Okay, let's see, the output use Y. Okay, so any sensor we can draw the output versus input function like this. So just now we introduced for ideal case, it will start from 0 and a straight line. Okay, that's an ideal case. But unluckily, we are in the real world. Okay, so in practical, most likely it is not cross 0. Okay, also not start from 0. Could start from somewhere here. Our sensor response. Okay, now we look at this in this more general way, and the response could not be a linear. Okay, could go up. Okay, at beginning looks like a linear, and it could be like this. Okay, some funny shape could happen, and it could increase. Okay, this is your real life response. Very possible. Okay, very funny shape. Our input-output relationship. We look at it in a general case. Okay, and this curve we have a name called calibration curve. Okay, it's real life curve. Okay, also we can call it a transfer function. Okay, so this is the first one, and it starts from the minimum value, which is here, and stop at the maximum value. Okay. So how about input value from here to here? We have a name called span. Okay, and sometimes we call it dynamic range. Okay, so span we use this term for some linear sensors. Okay, let's say if the force change from 1 Newton to 10 Newton. Okay, and easy linearly change, gradually change. But for some parameters, let's say the sound level, okay, acoustic level, it covers more dynamic range, can be very weak sound, okay, and can be very loud sound. It covers from milli unit to mega unit, cover large unit range. In that case, we use dynamic range. So most likely we use dB to represent it. Okay, that's decimal decibel units. Okay, this one sometime called transfer. Okay, I forgot function. Okay, now we finish this. We finish this. Finish this. Okay, and from this curve we can have some other parameters. How about sensitivity? Sensitivity we already introduced, right? That one based on the linear response, a straight line, the change of output over change of input. And how about in this case? It is non-linear, sometimes change faster, sometimes change slower. Okay. For this general case, let's say we have a particular point. We want to focus on this small range. Okay. Still, the definition will be still valid. So the change of input will get some output change. Okay. So the sensitivity will be this change over this change. Okay. This will be the sensitivity. At this particular point, the ratio will change. So delta y over delta x. All right, so this is sensitivity. We finished. So now think about the resolution. So what is resolution? So resolution is the minimum input change which is detectable. Okay. So in other words, the small change of the input, for example, at this point, if we change here, output we cannot have any detectable output information there. So any value smaller than this small change, output will have no information. So why it happens? So this is the calibration curve we test one time. And the next time, okay, the calibration curve or transfer function can move to here, okay, due to some errors, some drift, some other different effects. And our output could be anywhere inside this blue dashed region. Okay. So this one we call it errors. Okay. Okay, we cover this part, errors. So due to different imperfection factors, we can introduce this. All right. The noise will be the smallest change we cannot detect, right? Okay, this is the noise, and out. Sorry, it's not noise. It's due to the noise, and this is called the resolution, the smallest one. And output, this corresponding output could be the noise. Okay. So we have some relationship between noise and resolution, which is linked by the sensitivity. So which means sensitivity will be the noise over the resolution. Okay. All right. So we already covered most characteristics using this single graph. So give us some ideas about the different parameters we are going to discuss later on.